reality. Welcome to reality. Welcome to reality. Welcome to reality.
Hello and welcome to reality, where your host TechTranslate and myself, NOPEGENX, tackle the flat Earth misinformation spreading through social media. As I always say, I generally keep an eye on Facebook while TechTranslate is focused on X. So in each episode, we'll be looking at one subject and going through its reality with you. And this week, with my big head, I might have to move my camera a little bit. We're looking at gravity. So how are we doing, TechTranslate?
Yeah, quite good. Yeah, it was very interesting, this subject. I had to dive a little bit more in than I usually do. Okay, for the slides, which I present on X, I do it also per subject, but this were also a lot of different subjects, and it was very interesting. And I love to do this, no, by the way, and also make the slides to explain it in an, I hope, understandable way, no.
M2M has come to join us. Thanks very much for being here. He says, hey. Well, he actually says, hey. But okay. Hello to you. Thank you.
Okay, good. I think we start, no? Then
we have got a lot to get through. Last week was a little bit longer than we normally planned. We had it always intended to have this about an hour and a half, but we were dealing with quite a large subject, which needed a lot of motion, obviously, lots of different aspects of motion to cover, and it got a little bit technical by the end. Now, Tex, I've had a word, you know, and he's very kindly made everything a little bit easier to swallow this week. So we're going to let him take over with his presentation. If you've got any questions, obviously let us know in chat. And in the meantime, I'll keep an eye on things. But otherwise, here's Mr. TechTranslate.
Thank you. Good evening. So, gravity totally misunderstood. We planned this as part 1, Newtonian. So today we go only into Newtonian. There are basically, this is also the one subject the flat earthers always attack. There's Newtonian, but there's already general relativity. What is the right one? No. And so basically Newtonian is for the daily usage enough. And me as an engineer, I've learned in university only Newtonian, but I knew that there was general relativity. But when you are below 10% of light speed and you're not traveling around a black hole, Newtonian is enough.
I don't think I've been that fast just yet, so we can stick with Newtonian. Let's make that a bit bigger for you.
Yeah. Okay, and first let us see the phenomenon gravity. This is also what Newton basically observed. The apple is falling. We are used to see this. This is nothing special, yeah. This is what we observe. But when we think about this, it is wild. The apple is falling. It's on its own, no string. Nobody is pulling it down. Basically, an invisible force is basically pulling it down, according to Newtonian, of course. And and you cannot shield it, yeah. And there is also not anti-gravity or something like this. It is not possible also to produce artificial gravity only through centrifugal forces, but you cannot make a coil or something like this, like an electromagnet, to make gravity. No, it does not work. Okay, so this is one very common meme of the flat earthers. This is a helium.
They do
ball.
like their helium balloons, don't
the
they?
helium balloon is funny when you inhale it and speak. And they always say it is, it's obviously going up. No, so is this really a force? Yeah, it is a force. No, you know this hot air balloons. No, they are carrying people. There must be a force upwards. So what is it here? They say gravity is density, buoyancy, and electrostat. Oh, he put in everything.
Electrostatics.
Yeah,
Yep.
every words he don't know, he put in. Okay. Then here again, okay, something also with buoyancy. This is a very interesting one, by the way. Here you have different fluids with different densities and objects with different densities, and one floats here, the other here, and the other sinks down. So what else have you? Oh, this guy, yeah. So floating apples disprove gravity, and also ships, which is quite awesome. When you look at the ship, it's completely out of metal and obviously very heavy, but it swims, or floats.
Inequalities here.
Yeah. And this is a very interesting one, the video. I think it's the most interesting flat earther post. And I did not know that an anvil, I think it's called anvil, can float on Mercury. No, I did not know this, but I looked at the densities. Yeah, it works out. It floats on Mercury as like a ball of styrofoam or something. Not like this. It has mass. It's difficult to move, but you can move it. It's floating there. No, this is very interesting.
The density of the mercury is making the anvil act as if it was a styrofoam on a bit of water, sort of thing.
I thought mercury, because it's a liquid metal, that it is less dense. No, this was my thinking, but it's wrong. It's so interesting. So
it's got very tight molecules somewhere, hasn't it?
Yeah, exactly. And then electrostatic debunks gravity. There, I'm at home with electrostatics, and they before it was density and buoyancy. Electrostatics. Here you see what he's doing. He maybe rubbed the plates against each other or somewhere else, and they repel each other. No, this one goes up to his hand, and it goes upwards against gravity. So gravity is a hoax. And I like this one. Static force is the force between two objects of opposite electric charges. I think he mean electrostatic, but because static.
Yes, we'll let him off. Maybe this is one of Dirth's favorites, isn't it? Electrostatics.
In between two objects of opposite electric charge, we should tell him these are the same charge, otherwise it would not repel each other. And then comes the best one. I read it yesterday. I could not stop laughing. Dielectric acceleration is magnetic attraction. I didn't know this. Dielectric means non-conductive. Acceleration
means completely neutral.
So dielectric, so non-conductive acceleration, whatever it is magnetic attraction. So
so a non-conductive element is attracting magnetism. Okay.
So we should not stop with this one. We have more to do. So, and then this is where you can buy this on Amazon, a similar one. You spin basically this this, how do you call this? Gyro, no?
Or gyro, yeah.
And you have here a magnetic field. And gyroscopic, last time we had rotational movement, is very stable. And so normally it would, if you would put this magnet without spinning it, it would be not stable. It would go here or here. No, and by spinning it, it's possible to keep it here in an equilibrium, and it floats and turns. It looks really awesome. I thought I buy one on Amazon, but does it? Now it's magnetism. So basically, density and buoyancy, they say, is gravity. Electrostatic is gravity. Magnetic attraction is gravity, and so on. So
and they're pretty wrong about everything.
They don't make even. They put sometimes everything in one post, and okay. So first of all, gravity is density and buoyancy. Okay, we look now here into what is density. Yeah, and we have here the balls have all the same volume. No, this one is of lead. This one is of water. Okay, normally we imagine it stays inside a kind of balloon or something like this, and a styrofoam ball. And what's the expectation when we drop them? What's the expectation which is heavier? No, and all have the same volume.
I'm going for lead. I'm going for lead.
Yeah, right, lead. Then comes water, but I did not write it down. And at last, styrofoam. So basically same volume, different weight. Lead has more mass per volume than water and styrofoam. Yeah, and when you let this sink, this is density, mass per volume. So we say it normally, and so density is mass per volume. It is basically a feature of a material. This is like this ball is hot or cold. Yeah, so it does not have a direction or a force or something like this. No? And it does not cause something like this. No? It makes the object heavier, okay, but it does not something. No? And here with density, yeah, because I will write down it in short form later. M for mass, M for volume, and we always use rho for density because I think we were running out of the Greek letter, out of normal letters. So density is mass per volume. We said this already. And we write it down. Rho is density equals mass per volume. Yeah, per volume is basically divided by. Now this is, we say it casually like this, but if you have the formula, it's basically this. You have to think basically what it says, not look at the letters and say, oh man, that looks complicated. And very important units. Now, this is basically my first lecture in physics. We were tortured with this. And my professor said also, if you do not put a unit, don't calculate with units, you get 0 points. Even if the number in the end is right, it could be potatoes, bananas, you have to use the units. No? And in the end, you see also if you're right, when what you get has the right unit. No? So obviously for mass, it's kilogram. For volume, it's cubic meter. And for rho density, mass per volume, it is kilogram per cubic meter. So
M2M makes a very valid point that there's often a confusion between mass and density as well.
Yeah. And so basically, this is why do we need density? It makes it complicated. But imagine you have a container of 3 square meters. No? You want to put water in it. No? And how heavy will it be? No? Okay, you can measure it. How heavy is 1 cubic meter and multiply it with 3? This works. But if you have here the densities, you see lead is much dense than water. And when we have the density, you have mass per volume there. I wrote it deliberately now in the other way, because if you multiply both sides is the same. With V, the volume, you get the mass. And mass is rho multiplied by volume. And so basically, if you look this up in Wikipedia and you know your volume, then you can calculate the mass. Now, please don't confuse the mass with meter. When this is unfortunately, we have the same letter for this, but in this case it means meter, and here it means mass. So I hope this is not too confusing. So what is buoyancy? Let us see. This is a ball of lead. What's the expectation? I think, it sinks down. No? And it did not only sink down.
I'm pretty certain everyone in chat got that right.
Yeah, the water go up. When I do it again, okay, it displaces water. This.
And we shout Eureka. Yeah, is this our Eureka?
Yeah. This basically, yes. This is the Eureka story, basically. Yeah, and you see it displaced the amount of water as it has as volume. No, and what did you see here? You see it goes up. No, here's something going down. So you see something going up can be caused by something going down. Now, here it's only the water, and it's quite obvious that the heavier was basically displacing the lighter, the less dense weight. But in this, it is the same thing basically like a scale. You have on one side lead, on the other the imaginary ball of water, and you have here a force down because this is heavier, and here you have a force upwards. Yeah, this one causes this force upwards, and it's a real force. You can feel it. No, so gravity, I think here you see it is quite logical, can cause a force upwards. No, and this is very important when we come to the next slide, because I think with an object heavier than water and water goes up, this is more intuitive than when it's the opposite. But in the end, it's the same thing, but vice versa. Oop. Now we drop a ball of water, a ball of styrofoam into the water. Yeah. And the expectation, of course, it floats and it displaces only a minimum of water, no? And it floats, it dips a little bit in, and what it displaces here is basically this amount of water, and the force downwards when it's floating, because it's very lightweight, is very small. No? And when we have this, water went up, and this is basically the opposite as we had it before. No? Styrofoam on the left, water on the right. Water's heavier, force down, and it goes up. No? This is basically
that's buoyancy.
How what buoyancy is. It is not anti-gravity. It's not magic. It looks magic. Yeah, I remember when I saw as a kid a floating balloon, I thought this is something like anti-gravity or something. This was a miracle because it's counterintuitive. Yeah, normally objects fall, and when you see the different, you're puzzled. No? And here you see the force which causes it, but when you have the balloon floating, you don't see it. And here we do it with water because I think it's more intuitive, but the same works with gases. No?
Same with air in your balloon, isn't it?
Air, any gas. If you have a gas that's less dense, like helium, at the same pressure, no? Then the balloon is basically floating like here, the ball. And
the balloon goes up because the air actually goes down and around to the bottom of it, doesn't it?
Yeah.
And then lifting it up because it's actually going around it because it's lighter than the actual object moving up. Yeah,
exactly. And this
is it's heavier than the item using up. Yeah, this is still weight.
This is no anti-gravity. It's heavier. It does not fly away. Okay, when you push it very hard, it flies for a moment, but it comes down. No? But if you push it slightly, it does not go away because it is very lightweight. And of course, it causes also a small force upwards, but it's overpowered by this one. And basically, the sum of both are then the force downwards. So it reduces this force.
So M2M asks, basically just questioning that. So just like gravity, buoyancy must also be considered a force, correct?
Yeah, buoyancy is also a force. This is basically action,
like you say, you can feel it, can't you?
This is the action, and this is the reaction, basically. No, and and yes, it is the same basically with when people say pseudo force. They said to centrifugal force. No, I don't like it. It's also not that common. Now we say inertial force. No? This means basically you apply a force in the other direction, the centripetal, when you rotate something, and you feel the inertia. No? Here it's not inertia, but it's basically also a force caused by the force downwards. No? But this
if you need to know more about motion, then we've got our previous actual stream was about motion, and we'll explain all about the forces of motion in detail. So check that out.
Yeah, exactly. And so what is buoyancy? Yeah, it is an upward force caused by gravity. and the denser material pushes the less dense away, and in this case upwards, the water, or vice versa, the ball. I think in this way it is I think also intuitive, understandable here, denser than water and less denser than water. But if you look in detail, yeah, now some might think, okay, the water goes up, so the pressure is here higher, and that basically because of gravity, this is forcing this one up. No, we are in water, yeah, and if we are
sad news there, Tech. We're gonna have to start again. My friend Ford at a comedy show has turned up. She's saying hello, just got here, so we'll have to start over. I suggest we carry on and they just go back to watch it from the beginning at a later date.
Go back later to so basic. But I think this is also a good starting point to understand buoyancy, and so this forces the water up. But when you do it in a large ocean, yeah, it displaces it also to the side. So it is not really this effect like the scale. In when we do look in detail, we have a pressure gradient. This is also what that others deny. But everybody who dived, I'm a scuba diver, yeah, you have to equalize your ear every few meters. And you get, you see it, how fast you breathe the air away in your tank. The deeper you are, and when you are at 40 meters, you're breathing air at 5 bar. And this empties the tank very fast. It can only stay a short time. And there you see it's definitely a pressure gradient. It becomes, because gravity, water has a density, it has mass, and the more you have over you, the more it presses on you. And so
there's a dive limit, isn't there? There's a dive limit of around 40 meters, I believe, because of that pressure that you're referring to, that pressure gradient.
Pressure is not the problem. The problem is, first of all, the nitrogen narcosis, because at this pressure, nitrogen gets, normally it's not reactive, but at this depth, it goes in your bloodstream. And it feels good. I had this already. Because
maybe later.
Air only 30 meters, not more. Because when I go below 30 meters, everything became colored. I saw colored fish. I was in very great shape, but it's not possible to see their colors. When you pass 20 meters, there's only blue light. It's not possible.
A euphoric dive.
Yeah, with a different air mixture.
By Finding Nemo characters.
Yeah. Okay. So this was a little excursus. So basically, this is pushing harder on the bottom than on the top. Of course, lead is heavier than water, or denser than water, to be correct. And so the upwards force is smaller than the downwards force. And the entire weight is basically the sum of both of it. And all materials are lighter in water. And exactly how light? Exactly this volume of water which they displace, they are lighter. Now, this is diving again. You have this heavy gear and this gas, this air bottle. Now, it's really heavy on, but in water, no problem. No? And here, originally, I thought this is very easy to understand, but I thought a bit longer, and I think a bit too long, and sometimes you get crazy things out of it, because I thought, man, this is pressing inward, this pressing into the ball, yeah, but you have axial reaction force against it, so it equalizes the forces, so it would not go up. And I thought really long time. No, I thought on Tuesday to call you to postpone it, not because I wanted to understand this fully. And I thought, this is so. I looked in the literature, nobody tackled it. No? But then I found it's called, and then it was for me clear. When you push the car, you're applying a force, and if it has a little bit of friction, you have constantly to add a force, and the inertia you feel also. You feel that you have to push. And when you but you want to know in order to know in which direction it moves, you have to look which forces are acting on this car. And this is this force. This force is acting on you. And so this is the cause, and this comes back. And this is basically the same. The cause is this force, and it does not collapse. So this pushes the ball up, and this pushes basically in the water, and it's only the reaction of this one, and does not cause a motion of the ball. It caused the motion of the water. It pressed it away. No? It displaced it. No? So
I think that's clear, because it's very accurate descriptions about what goes on.
This is critical thinking. Yeah. Not
proper critical thinking, not their critical thinking.
Yeah. It starts with yourself. You see something, you question it, and think, boy, there's something I really don't understand in a very simple thing. And this is basically critical thinking. They think critical thinking is to say, you're wrong. Always it's flat, and telling other people they're wrong. No, you first have to question yourself. Maybe I say always, when you are the only one who thinks he's right, maybe you are wrong. And so this is you have to reflect yourself and and you basically know when you really understood it. And this is basically all how my oral exams worked in university. We are not indoctrinated. My professor would have asked me this 1,000 times, as he did not, but to simulate.
Hopefully not literally.
He wanted to know, why does it do it? No, this is not. No, again. Why? And until I thought, okay, it has to be this and this. No? And this is basically not indoctrination. They want us to think by ourselves and realize that what we thought we know, we did not really understand. This was also the case here with this one. And how does buoyancy? Okay, this is the same. Okay, this is basically the same with lighter than
with lesser force, isn't it?
Yeah.
It's got a lesser equal force.
Yeah. It has, and because it floats, it does also not move anymore, and it does not sink. No, the other one was staying on the bottom. No, so basically it would fall deeper. But here we have then, when it floats, an equilibrium. No? It does not sink. It does not. So this upward force and the weight are in balance, and the force is zero. It forces zero, then an equilibrium. So force underwater, buoyant force upwards. Okay. Yeah. Now, we had here in this example, it is floating, and both are the same. Now, when you force it underwater, what happens? You're displace
new force, aren't you?
Yeah. You're pressing here actively with your thumb or with the blue arrow or whatever, and you see these forces are now much stronger because you're deeper here because of the pressure gradient, and so the upwards force becomes stronger and strong. It becomes stronger. Yeah, this is basically, if you force it down, you will feel it will go up again. No, and this is basically the pressure gradient trying to push something away which has less density than itself and is lighter. No.
Brilliant. Yep.
No. So now buoyant force. Now we look a little bit how we calculate it. This time I don't go too deep into it. So basically, we just start.
So don't run away, everyone. We're not going to go into like 4 hours of detailed lectures
so
now.
Yeah. The force, basically, how is force defined here? It's floating. For Fg is the force of gravity, and this is the buoyant force. No?
And you need to be clear as well that the previous slides were taking those into consideration as well. We're just looking at like what flat earthers say without gravity, but in reality, gravity would form part of all those explanations, wouldn't they?
Yeah. And here a force is mass multiplied by acceleration. acceleration is the rate you become faster over time. No, and it makes sense. Mass has inertia. No, so the more if you want to accelerate something at the same rate and which is heavier, you need more force. And so basically, this is Newton's definition of force. This is also one of his laws, Newton's laws. And so how we calculate it? Fg is G is Earth gravitational acceleration. Maybe you heard it 1G, 2G, 3G.
Yeah.
When they fighter pilots also have to with this basically tells you how stronger the acceleration is, or the higher. No, and this is Earth's acceleration. So instead of A, we say G, and this is the mass of the object here. This one, and this is the gravitational force down on the ball, and yeah, it pushes the ball up. Yeah, and yeah, okay. So, and the buoyant force Fb is G, also Earth's acceleration, multiplied by water displaced, not by the mass of the object. The water which has been displaced has to put it here. But how do we measure the water displaced? We cannot. We can measure it. Yeah, we can here have a scale or something like this, and but we know the density, right? We know m rho equals mass per volume. Yeah, it's mass per volume. And if you rearrange it, so both sides multiplied by the volume, you have mass is density multiplied by volume. You get your mass back. And if you substitute this one, you have in the end the buoyant force. So this is Earth. It's German. I'm not used to TH that much.
I'm not used to speaking German.
Density of water multiplied by the volume displaced. How you get the volume displaced is basically the ball. If you put it complete underwater, here it's not completely underwater, but if it's completely underwater, the volume of the ball is the volume displaced multiplied by the density of water, and Earth's acceleration give you the buoyant force up. But that's not the whole story. This is interesting. They always say gravity does not exist. And you see all this equation have G, gravitational acceleration. So this means basically gravitational acceleration is how much you get faster over time when you fall. Yeah, when you jump from 1 meter, it's okay. When you jump from 2 meters, it's not okay. Yeah, and so basically it tells you how you get faster over time. Yeah? And they say this does not exist. Gravity does not exist. So, and if G equals null is 0, then the gravitational force would be null, is 0, and also the buoyant force. Why? You see, we have the multiplication with G. If this becomes 0, 0 mass is 0 force, and also gravity. 0 mass is 0 force downward. And so you see that gravity is even in the equation for the force upwards. It does not work without gravity, but it has the different directions. So in order to get the net force, so basically the resulting force, you have to the gravitational force, and from this you have to subtract minus the buoyant force. We use the minus because it has a different direction. I did not want to do it here with vectors, but this has a different direction. Therefore, we have minus. In this case, the resulting force would be 0 because it floats at the same place. No, but if we would push it down, Fg would be the same, but Fb would be stronger. And if this becomes negative, it's buoyant. And if this is still positive, like our ball of lead, it's heavier. That's basically the magic behind it. And this is basically how you directly can see when somebody is bullshitting you. Because you know this formula, and you know if there's a 0 in, also the point force is 0, and also you're flying around. Okay. So if some of you maybe noticed it, I use very often weight and mass in a synonymous way, but this is physically wrong. Yeah, weight always mass. So in Newtonian, the moon has the 6th of gravity of Earth. This is well known.
Yep.
So 1 kilogram on Earth is how much on the moon? 1 kilogram, because kilogram is the measurement of mass, not of weight.
Yes,
Yeah?
it's the mass, isn't it?
Yeah. So basically, our scale, which we use every morning, I don't use it anymore. It's so too depressing. It tells us basically our weight.
I know that feeling very well.
And the scale is in kilogram, because it is proportional. No? So basically, on Earth we use for weight always kilogram, even if it's physically not correct. In the correct way, we say Earth has 9.81 Newton. And so this is the weight force. We measure the force in Newton. We come to this in a few minutes, what Newton means. And the weight on the moon, this is a 1/6 of it, as expected. So the mass stays the same. You would feel it if you would push the ball. Yeah, this has inertia, and the same inertia on the moon. Yeah, if you would take a styrofoam ball, it would be easier here, and it would be easier here too. No, but here with the ball, you see the difference. No, here difficult to push, and even on the moon, the denser the material is, the difficulter to push, and this is because of mass. No, and the weight is basically how much force it is generating downwards. And basically, this number is quite well known. This is the G we had in the formula before. So Earth gravitational acceleration, we call it G, and it has 9.81 meter per second. What does this mean? This means per second, it becomes 9.81 meter per second faster. We use here the meter per second, kilometer per hour, miles per hour. These are all measurements for speed, and this tells you basically how much it gets faster per second. No? And on the moon, it's much, and you see it's the same one nearly. No, and when we see
obviously less gravity on the moon, so
exactly.
it's going to accelerate slower.
Yeah, exactly. And you have here F Earth and here I put in the 1 kilogram. So here's a 1. So this is here what I meant with units. Then this is the beautiful thing of metric units. Yeah, you can multiply division, not adding and subtracting, of course, but you can wildly rearrange it as long as you use the basic base SE unit, this kilogram, meter, not kilometer, and second, not hour. No, and second square means basically meter per second per second. That's why the squares here.
That's something they misunderstand, isn't it? When something is squared, they will times it by itself.
Yeah, it is
as
basically
opposed to per second. Yeah,
you could write this, leave this out, and make a how I'd say here a division bar, and below second. Then it would be more intuitive. Now then you would see, okay, meter per second is the thing you become faster, and here multiplied by kilogram, and this is an ugly long unit, and in honor for Newton, we call it Newton. Yeah, this is this one what is here, and the same basically on the moon, because it's 1 kilo. It is quite easy to calculate, but and this is basically why the astronauts on the moon can jump so high. And because
their downward gravitational acceleration isn't as fast, is it? So so their upward acceleration doesn't need to be as much in order to lift them off the ground.
Yeah, and this was actually difficult to walk, they said, because with every step you you basically went off the ground, and they developed also some techniques to easier move forwards. Now you have to walk.
Which is why you see
differently.
them bunny hopping around on the
Yeah.
moon, isn't
They
it?
said this
It's
hopping
actually
is the most
easier to hop.
one.
Yeah.
Than walking, and with these suits, it's difficult to walk normally, also on Earth, because they are very stiff.
They're clumsy suits. They've got a lot of stuff going
Yeah.
on in them.
Yeah.
You see the outer thing and it looks really big and it looks bulky from the outside,
Yeah.
but there's another layer inside of that, inside another layer, inside another layer.
Yeah.
They've got multiple layers on with various different pieces of tech equipment on there,
Yeah.
and some of it protective, some of it life support. And it's all layers upon layers upon layers, which is why it's so big and bulky, and
Right.
why it would be so difficult to walk, because obviously we're naturally bending our joints in order to walk,
Yeah.
all the way down to like our toes bending, where
Mm.
in a big suit where everything's protecting you and everything's big and bulky and protective
Under
and not
pressure,
so
no?
flexible, it's going to be hard to walk around.
Yeah, and they have also in the newer ones, they have also in the finger joints, so that it's easier to move, and in the arms, to make it easier to move. Okay, then
A space that'll come another day.
Right.
Space will come another day.
Yeah. And so weight is the force due to gravity. And this is Newtonian, of course. And this is very interesting when they argue with buoyancy and density. They always say the weight makes blah, blah, blah. Not always, but sometimes. No? But with saying weight, they say basically this one here. Yeah. And this is Earth gravitational acceleration and Earth's gravitational force. So weight is basically this one, G, the force down, the weight force on the gravitational force of Earth, we call casually weight. That's it.
Which is why in different places on Earth, things weigh different. So a mass of 1 kilogram can weigh different in different places on Earth, because the gravitational force is slightly different. And obviously that was tested when they went to and did the final experiment.
Yeah. It is
critical think way different mass object.
Also due to the how it's called, centrifugal acceleration at the equator, but it's very minuscule and it's very small. I made the calculation. Remember, it is 0.03 or something.
0.361, wasn't it, or something?
Like this, or meter per second.
I remember back.
It was very low. And because most important for the centrifugal force is the rotation rate, not the tangential velocity. And the rotational speed of Earth is very slow. It's one time every 24 hours. And
so it's good. It's good to remember that weight is the actual force due to gravity, as opposed to the mass. So a 1 kilogram weight is actually 1 kilogram mass. And its weight is calculated as 1 kilogram at a particular point where gravity is 1.
Exactly. Okay.
I'm learning stuff.
And very important, it works in vacuum too. So it can't be buoyancy. Yeah? You can do it on Earth in vacuum chambers. If it was buoyancy and density, it would work only in vacuum. It would not work. No, you have nothing pushing you up. No, these little arrows would not be there. No? And so everything falls. And
we could all float around if it wasn't gravity, couldn't we? It'd be great.
Yeah, and this is basically thank you. Here you see the acceleration, and here the force. What does it mean? This acceleration stays constant. If you make the mass heavier, the force is stronger, but the acceleration stays the same. So this means basically everything is falling at the same rate. Even a feather and a lead ball, or
just say goodbye there. M2M's got to go. So thanks very much for being for so long. Obviously, there's more to this, so please watch the rest of it in your own time. But thanks very much for popping in, and have a great weekend.
Yep. Goodbye. So, and this is basically why everything is falling at the same rate, a feather and a ball of lead and everything else. And this is first counterintuitive because we are used that lighter objects fall slower, but this is due to air resistance. And here I made a nice animation, I think, to explain it more intuitively. Imagine you have two balls of lead, each one 1 kilo. It falls down, expectation, both fall at the same rate. Then 1 kilogram, 1 kilogram again, you bring them closer together. Expectation falls at the same rate. You put them even, they're touching each other. They're not welded or something, only touching. Yeah, it's basically very, very close, like the last one, but closer. And the expectation falls at the same rate. And now you weld them together. Yeah, before they next to each other and touching each other, it was clear it falls at the same rate. And so, why
still the same rate?
And why should 2 kilo fall faster? Yeah, this is basically
because it's the same thing, isn't it? 1 kilograms welded
this is basically
together.
Also, 2 kilo, no, and it falls exactly like the 2 kilo block or the
so a greater weight won't move any faster.
Yeah, and this is also what in school was demonstrated. We had a long pipe with a feather and a lead ball or something heavy. I don't know what it was, and that we evacuated it, basically pumped the air out of it, and then when we pushed a small handle, both fall. You could see without air, they fall at the same rate. Okay, so masses attract each other. Now we come into gravitation. Masses attract each other for unknown reasons, and actually, yes, this is why. But this is basically with every physical phenomenon. We observe it daily, but why? We have theories, and this is why they always say, "Oh, it's only a theory." But this is the best we can do. We can observe, think about it, how it works. And I say always, it's not about what it is. It is about how it works. Yeah, you want to have a formula. How, for example, the formula of gravity of weight gave us the information that everything should fall at the same rate. This is basically the prediction it makes, counterintuitive. And then you make the test. Oh, really? It works. So it confirms your theory. No. And
gravity's been very well tested, hasn't it? Over hundreds of years. It's a scientific theory because it's a tested theory that has no better explanation, basically.
And theory is also different used than in casual language. When you say
scientific theories are very different.
How this happened, this means basically you think it happens this way. But here also it emphasizes basically that these theories are not the explanation why you have attraction. Yeah, and we have a formula how it's worked. And with this, we can do quite much. We can send rockets to the moon. We can fly with Voyager out of the solar system. This is all with basically the formulas which I show and which I came. It's obviously rocket science, but it's based on very basic things, basically. You know.
Are you saying I understand rocket science here, Tech? I'm impressed. Impressed with myself.
It's a bit more complex, especially.
Okay,
so
I'll save the application form for now then.
Yeah, so this is basically what Newton found out. Mass, everybody knew it already, but which he clearly observed and said what exactly is happening. So mass 1, mass 2, and you have a force between them, and you have r is the distance between them. And he found out that the force becomes bigger when the two masses or one of the masses becomes bigger, no? And it becomes lower when you put them far away, no? And this is, and even very strong, this r squared, so it decays very quite fast, exponentially, basically. And he basically, this is the gravitational constant. And if you have basically this formula and you multiply it with this constant, you get the force. And this constant, there's no way to determine it mathematically. This is measured, and still measurements are going on preciser and preciser, but it's not something you can calculate or something like this. So this is only by testing. But if we have it very close, and it works quite well. And this is basically,
if anyone's unsure about mass versus mass attracting mass, all you actually need to do is watch teenagers at a disco or a club, because they just like flock, females and males just flock towards each other. Not quite the same thing, I don't think. But Tech's looking down his glasses at me.
Okay, and here is basically, you look, it's the top view from the experiment, and because the force is very weak, the balls would not roll to each other. This is basically their memes always. They show something is attracted by a mountain or something like this, and this, but it's very weak. And when you put this horizontally, this experiment, the gravity of Earth goes all down here, downwards, and they cancel each other out, and only the sidewards force will maintain, and it's very slow. And here is basically a torsion bar which measures the force. And with this, basically, it was done. And this is a historical picture, basically, of this. This is the side view. This is the top view, and it was made in 1798.
1798, people. 1798. We knew this stuff since 1798 when Cavendish.
And now we're talking about gravity does not exist. And they made these measurements here and determined already quite good G. And with this,
so basically, in 1798, they figured this out, and we still have flat earthers who can't figure it out.
Yeah, and with this, basically, Newton calculated the orbits of all planets, of the moon, of all planets, and basically by knowing this, and he did it very precise already, And I wanted to see, you have, so when, as an engineer or scientist, when you see a formula, you don't look at everything. You look basically the distance, or you see it's by r square. Oh, it becomes quite fast less. And this is basically when you only see 1 divided by r square. If this would be the force and this the distance, it falls down like this. So at one, basically, if you have double distance, it's already, what is this, only a third or a fourth of as it was closer here. So double distance means it goes far down. And so basically, okay, here I wrote this in again, and this is basically the r square is in the bottom, so we know it works like this. So electrostatic.
So I think we've covered buoyancy and density and why that doesn't work. As an excuse.
And basically also how basically we discovered and experienced gravity, right? And how do we experience electrostatic? They sometimes say it's electrostatic and use other buzzwords. How do we experience this? Thunderstorm. This is basically electrostatic discharge. And
this is a good example of what electrostatic actually is. You can physically see this.
And it happens basically, you have strong up and down winds, you have ice crystals which are rubbing each other, and this basically polarizes the charge of water, of the steam, of air, of everything, the cloud basically. And then mostly you have discharges in the clouds. This is very often you see only a flash over you, or in the clouds, or between different clouds. And then sometimes, if it's very strong negative and deep, it attracts positive. It can also the ground can become positive, and it's discharges here. No, this can also happen, and this is the flash which we see when it hits a tree or something else. No, and
That's the ones they always use in films, isn't it?
Yeah, and you see when you saw a tree which has been hit by lightning, it explodes. Yeah, the water evaporates instantly. And I saw a few. I remember last year a tree. It was completely obliterated. No, it depends how much water is in the tree. It's different to different trees.
The age of the tree, of course, and size. But yeah, it's quite remarkable that some people actually survive being hit by lightning, because obviously it's our water inside our bodies would react in the same way, where it would heat up rapidly, and a lot of the times people have been survived because they actually earthed themselves through what they were wearing, as opposed to people who have actually fortunately been hit and got the consequences of it.
And I'm in high voltage engineering, and my professor always said, for the current for voltage, you are only a bucket of water.
Yeah.
And okay. And this is basically the electrostatic effect, which I think everyone saw it already. Or sometimes when you pull out your pullover, your hair stands up, and you hear even the discharges. If you have a wool pullover, you hear that's
crackling. Yeah.
And
if you rub a cat against your jumper and put it on a wall, or we're not supposed to do that, are we? Don't do that. Don't do that.
And then we have these effects here, which seems to work against gravity again. So how? This is they see something is going up, so gravity can't exist. But this is not the case. And you can have, depending on the charge, repulsion and attraction. But this comes now a bit more in detail. How does electrostatic basically works? This is basically an atom, the entire thing. So this is the core, and this is the shell. The shell is out of electrons. It does not look really like this. This is basically only to visualize it. In reality, it's like a cloud of possibilities where it is. But but it behaves like orbits of a planet. Yeah. They have the same features. This is why we make this theory like this and use things which we know from the microscopic world. No? And
easy to visualize, isn't it?
Yeah, to visualize it. No? And so what happened here? This is when you pull out your pullover. Yeah, an electron flies away. Especially electrons in the outer shell they need only a little bit energy and they fly off. No? And then you have here the positive charged core, 3 protons. They are same charge as each one is same charge as one electron, but the opposite charge. Minus.
Yeah, so neutrally is obviously it's got the same amount of negative charge to positive charge, and then when you pull off your jumper, you're losing some of those electrons, and it obviously means that there's now more protons, so you're positively charged.
Exactly, and here you have 3 protons and 2 electrons, so it is positive charged because this is you have more of them, and then there are also these cases. Some other, especially some materials, they have quite empty outer shells, and they like to attract for a short time an extra electron, which is a short time companion. It will go away later on. But also
they're quite promiscuous little atoms.
Also, this without anything is already a negative charge, and here the entire atom is negative charged, 4 electrons and 3 protons. No?
Yeah, and so essentially the atom has more electrons than it does protons, creating a negatively charged atom.
Yeah, and fun fact: if you rip all electrons away and have only the core and the electrons, this is plasma. They say always the moon is plasma. They say it because they don't know what plasma is. It's just a buzzword. But this is basically plasma. This can happen when extreme heat, like our sun, then they are in a very high state, and the hotter it becomes, and then they are ripped off basically. And then you have plasma. You have it in your lamp, not in the LED lamp, the longer one.
Fluorescent lamps.
Neon lights.
Neon lights. Yep.
I know. What is glowing? This is plasma. No, and this is plasma. So it can also work you can use it also in a harmless and good way. So the electromagnetic force. We always say in science it's said electromagnetic force because electric force and the magnetic force have a similar origin, but they are different. And they're not the same. And now we explain what. Two types exists, positive and negative. We saw this already with electric charges. No, it's positive and negative. Then the forces can be attraction between positive and negative. Negative and negative repel each other, and positive repel each other too. So you have two different charges, two different forces.
Yeah, I remember playing with magnets at school doing that. Yep.
And now we come to magnets. Magnets comes only in a double pack. You have only dipoles. You have a single one. You have only dipoles, consisting of north and south pole.
Oh, so this is what I'd have played with is a dipole magnet.
Yeah,
and that's something that they get confused about, isn't it? When they talk about electric charges, they presume that they act the same way as dipoles, but
they mix them
not the same.
Totally up. No, this is very often. And here, when you cut this, you don't have separate charges. If you cut it here, this will immediately become a south pole. No, and this will
become a north pole. Yeah, or a negative source. Yeah.
And here you have similar things: attraction north-south. Then you have repulsion north-north and south-south. Now this is basically also. You have dipoles, two different poles as dipoles, and two different forces. So now electric field and magnetic field, they always use fields and they don't know what it is.
They think they're just where cows live.
Yeah, the electric fields, they think of something esoteric or something like this. This community, they think this is something spiritual, but in the end, it's only the way where the force goes. But I explain this. So an electric field is how the electric always between electric charges. They are monopoles.
West Side Girl Reacts asks, "Sir, may we play with the Mercury next?"
With the Mercury.
What do you advise, Tech?
With the anvil, which was floating.
No, I think they just want to play with the Mercury in this science class. I don't think they should be playing with it.
It's quite toxic. It is, also
don't drink it.
This example here with the anvil in the in the bucket there of mercury. This is actually very dangerous what he did. Now, I hope he was wearing protective stuff because this evaporates.
Don't stand in it. Don't breathe it. Don't touch it. Basically, the answer is no. West Side Girl Reacts. Do not play with the mercury.
Yeah, and if it gets, this is heavy metal. If it gets into your body, you don't feel it immediately. But the problem is, our body cannot sort it out, and it over the time. I'm not a doctor, but it causes some effects. No. Okay,
it's not good for you. Leave it alone. Put it back in the cupboard.
Yeah. So electric forces, as we said, monopoles, plus and minus, and we have always a source and a sink. Plus is the source, and minus is the sink. It's defined this way. We could have defined it also in a different way, but it has been. We had two choices, and we have no closed loops. We have always a beginning and an end. please don't think that they are that you have really arrows between them or field lines. Something my father thought this. I told him, no, there are not lines. They are visualizing. If you would put here a small negative electron, it would. This is basically the way of the force. It would go this way, and also in between, it would go this way. So, and they are. Basically, this gives you the information of the direction where the force is working, and the density of the arrows here more at one place mean the field is stronger. And you see, the closer it is, the stronger it is. No? And this is when they repel each other, they try to go away from each other. And if you have a single one, it's radial, and with minus, it's opposite, it comes down here. So, and when you look at magnetic field, here the origin are electric charges. For magnetic fields, it's are moving electric charges or magnetic momentum. I explain later. We have dipoles, north-south. We have closed loop, no sink or no source. Every magnetic field line is a closed loop. And this is an electromagnet, and this is why moving electric charges. This is basically where electric fields and magnetic fields, or magnetism and electrostatic basically have the connection. Here's the minus pole, electrons are always minus and go to the positive, and it would go as a spiral. It causes by its movement a magnetic field. Now, and honestly, nobody knows why. It is the way. This is like gravity. It's a phenomenon we.
They don't know why, but it's observable, isn't it? You're saying they don't know why, but it's something that can be done and observed, or proven, as they like to say.
And I said,
where's your evidence? It's there.
The closed loops, and you might say, "Hey, here I have sources," no, but we have to look at it are closed loops. Now you can say, okay, yeah, you just make this here translucent, but it works this way. Every metal, everything is out of atoms, and some metals have atoms with a magnetic momentum. What does it mean? Simplified, more electrons are circling in this direction. Very simplified, by the way. So it is similar to this one. Yeah, they circle and they cause a magnetic momentum in one direction. And if you have another one, it will automatically align by the magnetic force. They both attract each other, and then you have the line which is going through it. And this is basically the permanent magnet. And yeah, this was, I think you asked this yesterday, Nope. If you have here, electric charge causes magnetic field. Could I put here a coil and have infinite power? That's what
I like to save money. So
as a child in school, I think I was 10 or 12, I read something about magnets, and I saw something like this, and I said, it has to go vice versa. It does not work. But if you change oscillate, if you changing a magnetic field, stronger, weaker, this will induce an electric current. So basically, you have to pump energy in by constantly changing this, and this is basically what happens.
Which is why you can't have perpetual motion, because you're using as much energy as you're making.
Even if it looks like that it could be reversed, but it is not reversible, you have to put power in. And this is basically how a generator works. There are spinning magnets, and they are spinning next to coils, basically. And in these coils, they induced by spinning, you have to say they spin like this around. They every time they pass, they change the field here. Now you have to change the field, then you get current here out. This is basic of the one. And then
give up the perpetual motion, because it just doesn't work.
Yeah, this is basically, as I said yesterday, this is one of the strictest laws in nature. Every time the most interesting perpetuum ideas, they don't work. Yeah, and this is a law conservation of energy. Now, it cannot be broken. No.
So
And
all those TikToks that you may have seen,
Yeah.
just ignore them.
Yeah.
They're rubbish. They
Exactly.
don't work.
Exactly. Fun fact: energy cannot be produced or destroyed. It can only
There you
be changed. Yeah, you can change here by changing the magnetic field into an electric current, and then you drive a machine. You change it into mechanical energy. No, and the main mechanical energy. So basically, it never goes away. You can only change its state, basically. No,
Mhm.
but it. Yeah.
And if you want more mechanical energy, or for it to continue, you need to then pump in more energy. So essentially, you're feeding it, aren't you? And
Yeah.
that feeding something doesn't come from nothing.
Yeah, and why don't we build with electric charges motors? Theoretically, it would be possible, but if you make the charge at a certain strength, you will have an arc through everything. Also with vacuum, it has to be strong enough, then you have an arc and it discharges. You don't have the problem with magnets. You can make it as strong as you can, and electric motors can be very, very strong. Yeah. So.
Brilliant. I hope everyone's following this. It is quite detailed, but it basically, what we're doing here today is showing why these excuses that flat earthers use is as something that can be in place of gravity. It doesn't work because without gravity, that they don't actually have the same effect.
Yeah. And here now we compare electrostatic force with gravity. Gravity we have explained now, and electrostatic too. So electric field between electric charges, we know this already, source and sink to monopoles of two types. Same. And the force is, okay, this were basically both charges divided by r squared and a constant again. And okay, this is the constant. You don't have to look too deep into this. This are natural constants, and they are always crazy numbers. This is always the same. So gravitational field, it is only towards a mass. You have only a sink, no sources. You cannot have a source would be anti-gravity. As far as we know, it does not exist. Only sink.
Okay.
And
Before
only
we go further, Tech, just one quickly there. West Side Girl reacts in class has turned on her Bunsen burner and feels a little lightheaded. Well, I've told her not to light any matches for obvious reasons. And do you think we should take her to the nurse to give her some oxygen, maybe?
Yeah.
Or
lightheaded. This means was it methane or butane? Something like this.
Yeah, it's a Bunsen burner, so it's probably butane gas, isn't it?
Yeah, for precaution, yes,
Butane.
because if you feel lightheaded, it is basically you have less oxygen in your body. Yeah, so basically,
open a window, everyone.
Yeah, of course. This is the most important thing. Open a window, and it is very
Step away from the Bunsen burner.
Very fast. So 2 windows open and it goes away. Okay.
She's trouble, this one. She's in class watching, but she keeps messing around with things.
Yeah.
I'll keep an eye on her. You carry on.
Yeah. So and we have only monopoles of one kind, and this is mass. And if we have 2 monopoles, gravity with the same gravity, the gravitational field would look like this, and objects would basically follow these lines. And here they would straight fall down. Here they follow these blended lines because they are influenced also by the other mass. And and this is basically mass creates an attraction, gravity, only by its presence. It's gravity. Now, as far as we know, this is the case. No, this is wild when you think about it. That something is only there, and it creates a force. No, this is We experience it every day, but it's interesting. So gravity versus electrostatic, which is stronger? Some of them say even that the electric force is stronger, a lot stronger than gravity, so gravity can't exist. And some say that electrostatic, it is so strong, so gravity could not exist. Even if it exists, it would be overpowered.
Yeah.
And now we take a look. Gravity versus electrostatic, which is stronger? The yellow one is force electromagnetic, and the red one is force gravity. This is an electron, this is a proton. And this has a mass, proton has a higher mass than electron, positive mass, both have electron mass and positive mass. And here, this one has a minus charge, the proton has a plus charge. The charge have the same absolute value, but different, here this one has a minus. No? And so basically the field would look like, but right now we are looking only to the resulting force. So, and the second force is the gravitational. So basically we have these two fields here. So this is how we calculate the electric force. No, this is the charge 1, this is Q1, and Q2 is the other charge. And this is a constant, nature constant, and also divided by r squared. And we know this already from gravity. We have the same mass multiplied by mass by r squared. So they decay at the same rate. And yet now let's show which one is stronger. Okay, this is the don't look at this gravitational constant. They have all been measured. Now this is not something you can find out by math. You have to measure it with very sensitive equipment, and it's still done. Now we're trying to get all of this more and more precise. No? So in order to know which is stronger than the other, we can say electric force divided by gravity. So how much is the electric force stronger than gravity? This basically means if we say how much does this fit into this one, no? And we do this, EM divided by F, the force of gravity. And now we take the absolute value. This I added. I forgot the absolute value yesterday when we run the test. And basically now we put this here, and this basically is this one here, and there are the R2s on both sides. When you divide by this, you have to turn this upside down, so the R squares are canceling each other out. The rest is multiplied. You have M comes down here, and in the end you end up with this. And if you put in the values, these values in, don't look too close at this. I did this in Excel. Yeah, with these values, it works. You get this number. So what does it mean? 10 to the power of 39. This is a 1 with 39 zeros. I don't know how this number is counted. This is very big. So electromagnetic force is magnitudes stronger than gravity. So the flat earthers are right. No? So gravity, it's laughable. It's ridiculous weak. No, it's ridiculous weak. And okay, there I wrote.
But we're not over yet. We're not done yet. We might be getting beaten up, but
in the literature you find this value because they do it between two charges of same mass. Here I use different mass, therefore it came a little bit higher. So does the stronger force debunk a weaker force? You see here, I think Sylvester is a little bit stronger than this guy, and we would not say no. There is no force. He's putting force against it, but he is stronger. So basically, this is why he overpowers it. And but we saw it is magnitude stronger. What happens? Yeah, and even it decays at the same rate, both by r squared. Now, it goes down for both like this. So, or even at the distance, it should be overpowered.
Oh no, we're losing. So electrostatics is better than gravity.
Yeah,
there's a stronger force anyway.
Yeah. and gravity versus electrostatic force. And now we look, why does, I said this already, gravity overpower the much stronger electric force on large scale despite being so weak? So we remember we have two different charges, two types of forces. We have attractive and repulsive. And plus and minus cancel each other out. Yeah.
Oh, poor electrostatics.
Yeah, yeah. And you saw the lightning. The force is so strong. As soon as you basically put them out of each distance between them, the force is so strong they want to go together again. Now, and therefore you see the lightning, and everywhere you discharge charge something with full power, it tries to. This is basically how electric current works. Yeah, this is basically the minus charge wanting to go to the positive charge. Now, and we can drive machinery, everything with it. So strong is the electric force. This is basically electricity. Now, but it cancels itself out because it's so strong. No, and I didn't know. Oh yeah, and this is basically I don't know why I put in this here, but we'll see. And this and for Mars,
we have a little atom to show some electrons and protons.
And for gravity, we have only one type, with only mass, which causes it. We have no negative mass, no positive mass. We have only mass. And we have only one type of force, only attractive. No repulsion or anything else, only attractive. And so mass and gravitational force only add up. So basically, the more you put together, the more planets, the more suns in the galaxy are, the stronger is the force, the gravitational force. It always adds up. And the electric force, also when they are close together, if you go far away, this field would be negligible. It cancels each other out on a large scale. No? And normally the force is so strong that they would slam into each other. And if stars and galaxies would be charged, they would slam into each other directly. Now, they would fly with light speed to each other, and they are apparently not. And so we know the universe is on large scale neutral. So basically, it cancels each other out, and only for a short time, basically, we can rip them apart. I know why I put in this here. You see here, this one, normally they are repulsive. No? But here you're sticking together. This is another force. This is called the strong core force. Yeah, in German I know it only. This force works only.
What's it in German then, Tech?
Starke Kernkraft.
I love the German language. Go on, carry on.
It's one word. And,
exactly. It's just like one word. One word describes so much.
Yeah. And no, I'm in German again. So, and this force works only basically to a distance like an atom, but is much stronger, even like the electrostatic force. It's much stronger, but only a short distance. So if you bring these two atoms together, closer and closer, at a certain distance, they will snap together, and a large amount of energy will be would come out, and this is fusion, at nuclear fusion. Hydrogen bomb, or our sun does it every day. The gravity is so strong because the sun is so big, it adds only up, and it's so strong that it is at the local part. The pressure is stronger than this one. Because it sums all up and it pushes it together, and we have fusion, and we get energy out of it. So, and this is basically gravity overpowers the magnetism on the large scale, because EM cancel itself out. And when something cancel each other out, the weak one will win. Yeah.
And that's why electromagnetism is not going to replace gravity, because when it actually becomes on a large scale, those little demonstrations that Dirth puts on his videos of like a little thing on his desk moving up and down. It doesn't work on a large scale because of what we've just explained, or I should say what you've explained in detail there. And so every time flat earthers try and say that, try and remember this. It doesn't work on a large scale because it cancels each other out.
Exactly. And this is so last but not least, this came in my mind today. I made this slide quickly.
I haven't seen this myself yet, so hold on, people. We have an exclusive.
This is because it's related to gravity. What defines up and down? So they always post this that the people would fall off the Earth in Australia if Earth would be a globe, no? Because there's down. And but we saw already down. The gravity goes always to the center of Earth. No? So basically, you would have to flip this out upside down, and so down is on the Earth. It's towards the center of gravity, no? And there is no universal down. Yeah, down is
there's no. You can't define it on a ball because everything is going to the center. So it doesn't matter where you are on the ball. You're always going down to the middle, aren't you?
Yeah, and our senses are also the work on acceleration, the acceleration of Earth, and it cannot distinguish between the acceleration of Earth and centrifugal acceleration. This is a centrifuge for jet fighter pilots. Now they are swirling around. Here also long German word. This is Hochleistungszentrifuge.
Is that just the word centrifuge? Is it?
It mean very strong centrifuge, and this is why it's so strong. They had to make this so long because the word was so long. No? So
otherwise, if the Brits had built it, it would be like tiny, wouldn't it? It would just have centrifuge written on it.
Or you split the words, you would have two, maybe, So it's here from the from the Luftwaffe, here from the Bundeswehr, and here you are swirled around and you feel the centrifugal force. And what happens is basically you still have your gravitational force. It will go down, and the centrifugal force would be in this direction. This is the centripetal force. Basically, this holds you in place, but you feel the inertial force, centrifugal force. No?
You can see actually in that picture that the capsule that the pilot is actually sat in is actually now rotated at 45 degrees, isn't it? Because of those two forces working in action.
Yeah, and because we cannot feel two forces at the same time, and they basically overlap. And this is how you calculate it. If you have the length, let me say 2, and here you have 3, then you draw this one. This is basically vector calculation, and you get the resulting force. It is stronger.
That's the bit you feel, isn't it?
Yeah, this is the one you feel. And for this guy, down is here. No? These things are also completely blocked. They don't see anything. Yeah, and they feel
a little screen, don't they? And that's about it.
Stronger. And this is basically the only way how we can produce something similar like gravity. But we cannot produce something which is non-motionless and has gravity. And this attracts nothing. This is only the inertial force, no? But it feels like down, and this is basically the perceived down, and the perceived down is the sum of all accelerations.
Yep.
And this is because our ear. We have here Gleichgewichtsorgan. This is I don't know how it's in English.
Oh, we're moving into biology, people. We're going from physics to biology. Hold on.
I think there's water and nerve sense, and it detects with the water your direction in space. And because water is attracted by gravity, it will always tell you where down is. No? And when our eyes help too to see where down is. So when you're on a ship and it's moving and you're inside, you get sick. Now, because your eyes tell you you're not moving, but this one tells you, boy, you're moving, and our brain says, my God, something is not wrong with you, lay down. You're ill. No? And then, I'm not a doctor, but I found then this one. I'm not sure if this is right, but what I see here is x-axis, y-axis, z-axis, 3 dimensions, and each one connected by nerve cells, so that we feel each direction. I don't know if it's really this guy. I'm not a doctor, but it looks like this. And everyone is. You see also the waters here and everything is connected by this nerve cells. No, and this is very interesting, by the way. And this is the reason why he feels.
It's not the most sensitive piece of sort of instrument, though, is it? You know, everyone says about we would feel it, we would see it, we would hear it, etc. But unless those bits of water are moving around and the nerve engines are working exactly how they should do, you're not going to feel anything. You know, so it's only when you actually feel that that acceleration.
I forgot this. This is quite easy also to. This is basically vector calculation. It is basically trigonometry. No, this length is exactly like this length. Yeah.
Just say thanks to West Side Girl. Thanks. She's having to knock out. I understand we go on for a good hour in this stream, and it's obviously a little bit much at times. But thanks very much for being here. It's been great. Well, thank you very much for coming, and you've been nearly done.
Yeah, we are also nearly done. And basically here, this is Pythagoras. F resulting squared is Fg squared plus Z squared. This is trigonometry. Now, and this is basically the resulting force is not stronger than it is stronger than each of this force, but it's not the sum of the value. No, it is in between. No, because this goes in this direction and this and this. Yeah.
And there you go.
There we go.
West Side Girl left too early. She I bet she did that in class as well. You know, duck out early. No, it's been great having you all here, and thanks very much for sticking through it. It's a lot, but it needs to be said.
Yeah, and this is the teaser for part 2. So we did.
If you thought this one was a difficult one,
because now we went to Newtonian. Next time we want to go to general relativity, and I think this would be more interesting and easier to follow because I don't know most of the formulas. I learned only Newtonian, but I know how it works, so I try to explain it most in an intuitive way how to understand this.
Can we have cartoons next time?
Yeah, exactly. I make cartoons. And because special relativity, it is difficult to calculate, but to understand it, why it is not that hard as it's not counterintuitive, but it's I think the basic everybody can understand, and this we're going to tackle next week, and we come also to the black hole. This here, the one from Interstellar, and I will tell you why it looks like this. This is also
brilliant
of general relativity.
Well, thank you very, 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 very much. I hope everyone's managed to enjoy that. These streams are a little bit lectury in times, and we try to make it as interesting as we can, but obviously there's an awful lot of actual mathematics that has to be put forward to show why it's misunderstood, and why we always say that in all of our titles that it is totally misunderstood by flat earthers, because they don't actually understand the mathematics and everything behind it. And I don't, you know, tech teaches me a lot every single week, and it's always fantastic to watch. And so thank you again, Tech.
Explain it. Now, this is in school, in university and in school, I worked also to earn extra money as a, how's it called, a tutor, for people, for children, for example, who were not so good in math and I like to explain it. And I saw, and when you see clicking it in their brain, they understand something. This is really rewarding. This feels really good when you see, somebody got it finally.
Well, I got it. You know, the good thing about what you do is it may be quite heavy and it may be quite lectury to some people, but it's actually actually very intuitive if you follow along. Okay, so if there's anything you don't understand about what you've seen tonight, we'd always suggest rewatching parts of it. You know, we can cut it up and just watch the bits that you're unsure of, because all the information is there to show that, like, it's proven and shown as to why gravity exists and why buoyancy, density, electrostatics don't answer the questions.
Okay, and then I will shortly advertise my. If you like my stuff, come to my site here on X. I post quite regularly. My name is TechTranslate at TechTranslate_G. But if you type in the search field TechTranslate, you will find me, and you find my posts here. Under highlights, I put the best one which I had, debunking. Here I photographed the sun. Here I explained why airplanes don't have actively to dive.
Did you want that on screen there, Tech? Because it's not on screen.
It's not on screen.
So, 1 second, I'll bring that up again. There you go, my friend. Sorry.
No problem. Okay, here, TechTranslate_G, or just TechTranslate, you put it in here. And if you click on highlights, you see some of the slides, something I explained here. Here I explained, for instance, why pilots don't have to dive the nose down to follow Earth's curvature. And similar things here I explained. I was very lucky. I made this picture. I thought always how people make such pictures, and it was coincidence. And I was fast enough on the shutter. And
it's a great picture.
Yeah, and as I said, a lot of debunking, and I would be happy if you follow me, and if you click
please
the
do.
like here, and this would be very nice. And you see
these streams, just so everyone knows, these streams are created basically because I found TechTranslate while wandering through X, and we got to chatting, and obviously we have the same views, but Tech knows a lot more than I do. Hence the reason I call him Tech, not TechTranslate. But please do follow him on X, because the information he has on there and his slides and the way that he breaks it down is actually spot on to how it can debunk anything that any flat earther can come up with. Please follow him.
Yeah, thank you. So
absolute pleasure, and thank you again. Let's put you back on there so you can actually see your face. There he is. There's the man himself.
So
and there's my big ugly mug.
Can I show my mug here? Do everybody? Yeah, this is basically the equations which are all behind it, the Maxwell equations for electromagnetism. And this mug was not allowed to take it into the exam because they expected us to know these all. This is a real story. And this is a very nice mug, and basically everything about electricity with this formula, not quantum physics, but the larger scale, like electric motors and things like this, you can explain with these formulas, even radio transmission and things like this. No?
It all makes sense when you know it, doesn't it, Tech?
Yeah,
absolutely. And thank you again for an absolutely fantastic stream.
Yeah, my pleasure.
Obviously explaining things in detail so that you can watch and understand it. And again, if you're ever unsure of what's been described, drop something in the comments, get hold of Tech in X, ask him directly. I'm sure he'll be happy to explain it in detail. It's kind of his thing. So thank you very much for that. Unless you have anything else you'd like to say there, Tech, I think we're going to call it a night.
Yeah, I think it will too. Yeah.
Hour and a half of lecture, but a very interesting one, debunking all of the misunderstandings about gravity. So thank you very much, and until next time.
So goodbye to everyone. Okay.